Let's go ahead and look at liquid dominant geothermal resources. So in liquid dominant systems, water is available at 150 up to 315 degrees Celsius. If the pressure is reduced, the water will flash into a two-phase mixture of relatively low quality, hence the name liquid dominant. There's basically three system configurations for this are possible. What we would call flash, binary, and total. Here is an example of a flash system. In a flash system, hot brine from a geothermal well is brought to the surface where the pressure is reduced and some of the liquid is flashed into vapor. So we have here a supply well with liquid water at a high temperature and a high pressure brought into a flash separator. So the pressure is dropped significantly as it goes into this flash separator. The liquid that remains gets rejected back to the ground, and the vapor resulting from the flashing process gets pulled and put into a turbine. On the TS diagram, we have the following. We have, again, we'll assume a saturated liquid of some sort. Goes through a separator process, a state 3, right? And then what's happening is that state 3, the liquid gets rejected back to the ground, and then the saturated gas gets pulled over and gets pulled through, gets put through a turbine. Once it goes through the turbine, again, it goes through a direct contact condenser and recondensed, and the condensate's rejected back to the ground. So let's go ahead and look at an example problem for this. Example problem reads, a geothermal power plant is supplied with water at a well bottom temperature of 225 degrees and a pressure of 8 megapascals. The fluid flows into a flash separator maintained at 40 kilopascals. The turbine exit pressure is 10 kilopascals. The overall efficiency of the turbine is 83%. Calculate thermal efficiency, the heat rate, and the steam and water mass flow rates required for an output of 10 megawatts. So let's take a look at this. Starting at state 1, here we have water at a pressure of 8 megapascals and a temperature of 225 degrees Celsius. So here we get our enthalpy. In this case, it's about 969 kilojoules per kilogram. And again, we're going to assume an isenthalpic expansion process through the separator. Where state 3, when we're inside the flash separator, again, the pressure drops down to a low 40 kilopascals, and the enthalpy is the same as it has been when it was pulled from the ground. So once it gets to that point, you'll notice that the quality is 0.281, okay? That's important because that means that 28.1% is going to be vapor, and that goes to driving the turbine, and the rest of it gets rejected back to the ground. So if we look at this, out of this quality, the gas enthalpy, which is going to get pulled to the turbine, is 2,636.1 kilojoules per kilogram, and the water enthalpy, or the fluid enthalpy, the saturated, actually I'm not going to pull that in because all we're interested in is the gas enthalpy. So we have the gas enthalpy, all right? So again, that's not the total enthalpy, that's the enthalpy, the portion of that saturated mixture that's gas, and that will get pulled to the turbine. So we have a gas enthalpy of 2636.1 kilojoules per kilogram, and we'll also go ahead and take a look and pull out our entropy, since we're going to be analyzing the turbine. So that would be 7.667 kilojoules per kilogram Kelvin. So here we have, coming out of the flash separator, state 3 at gaseous state. Okay, so just again a review here. In the flash separator, we have the gas that goes to the turbine and the brine, the fluid that gets put back to the ground. So the state of that gas getting pulled to the turbine, we just went ahead and computed. So we have, we'll call it H3 gas, so 2,636.1 kilojoules per kilogram with an entropy of 7.667 kilojoules per kilogram Kelvin. Okay, so state 3 to state 4 isentropic. We have the pressure coming out of the turbine, 10 kilopascals, and we'll assume the entropy to be the same for the isentropic state. That gives us an exit enthalpy for the isentropic process of 2,431 kilojoules per kilogram. So that gives us an isentropic work of the turbine of 205 kilojoules per kilogram with an actual work. Take the efficiency, multiply it by that, an actual work of 170 kilojoules per kilogram, which would give us a mass flow rate of steam. It would be the work that we want divided by the actual specific work, right? So we want 10 megawatts divided by our actual work of 170 kilojoules per kilogram gives us a mass flow rate of steam of about 59 kilograms per second. And then it's also asking us to find the mass flow rate of water, right? So what would be the mass flow rate of the water? Well, coming from the ground, we would just basically take the mass flow rate of the steam divided by the quality through the separator. That tells us that in order to get this 59 kilograms per second of steam, we have to pull about 209 kilograms per second of water from the ground. So again, that would be the water coming from the supply well. Ending this is asking us for the efficiency of the process. So if we were to look at the specific work over the enthalpy difference between it coming from the, we'll go ahead and look at the enthalpy difference between coming from the supply well and being rejected back. You're plugging your numbers there, we would get about 19.3%. We can also go ahead and compute something called a well bottom efficiency, which basically takes mass flow rate into account. If you go ahead and take the mass flow rate of the steam, multiply it by the specific work of the turbine, and divide it by the mass flow rate of water times the difference in enthalpy between the well bottom and that being rejected back to the ground, we would end up with, in this case, 5.4%. So again, this is for a geothermal a flash system.